Okay, so for day 3, we're going to continue our applications. You're going to notice some of them are very similar to what we were doing yesterday. So by the end of today, you're going to be able to find the resultant forces, and we're also going to be talking about tension.
So it's just a force instead of a wind.
What's that?
So it's just a force instead of a wind.
Instead of the wind, yeah. Okay, so for example 1, it says a man pushes a lawnmower with a force of 30 pounds exerted at an angle of 30 degrees to the ground. Find the horizontal and vertical components of the force. So if you're finding the horizontal and the vertical components, really what you're finding is the vector. Because in a vector, you're going to have horizontal and vertical components. So when you think of a person pushing a lawnmower, we're going to draw out the picture.
Sometimes the directions confuse me, like the 30 degrees to the ground.
Yeah, yep. Okay, so let's imagine a person pushing a lawnmower. Okay, do your parents make you guys make you mow the lawn?
Yeah, then I told my brother it was kind of fun tonight.
Yeah, my dad wouldn't let me because he's afraid I'd ruin the grass. So think about when you are pushing the lawnmower, right? This is how you're pushing it so that it's going forward. So we're going to make that our vector. Yeah, it's in the downward motion, right? So here's his hands reaching out. This is our lawnmower, which is going to be our vector. Okay, which is a force of 30 pounds exerted on it. Now, every single vector has a horizontal and a vertical. So we'll make his legs a little longer so he isn't floating. Okay, and then here's our horizontal component, and here is our vertical component. Okay, so to figure out our vector, this is going to be 30 degrees with the ground. So think about, okay, this is the ground, here's my force.
So that's theta?
Yep, exactly. So this is our vector V, and our vector
It's 30 cosine 30.
is going to be the magnitude cosine of theta, and then the magnitude sine of theta. And our magnitude in both cases is going to be 30 pounds. And then we're going to solve. Okay, and we know the cosine at 30 because that's an exact value. It would be root 3 over 2. And the sine of 30 would be 1/2. Now, just to make it easier, you guys can always round to the nearest hundredth. I would not mark you wrong though if you had 15 root 3 15, that would be perfectly fine. Or you can round to the nearest hundredth and have 25.98 15. Okay, so either one of those vectors would be correct. All right, so going to example 2, this is the one that I asked you to start, and they drew a picture for you, but I always think it's helpful to draw my own picture so I can get a sense of what's happening in the problem. So it starts off saying that a river flows due south at 3 miles an hour, okay? And this you could either choose to put on the grid or off the grid, it just depends. And again, if you are in physics, you probably are used to drawing it off the grid. But if I'm going south, that means the river is flowing straight down. So here's my river. Okay, and the river is flowing 3 miles an hour. And then the swimmer heads east, swimming at 2 miles an hour relative to the water. So when it says relative to the water, that's the same thing as like the plain and still air. So this is how he's swimming.
Without force.
Yeah, exactly, without the river force being acted upon him. So this is 2, and then I'm going to label this as S. Now we're going to talk for a minute about resultant vectors, which is something that we covered in the first day. If the river is pushing you south, okay, because that's where it's going, and you're going east, if you have the south force upon you, do you guys agree that his direction is going to be somewhere in between these two?
Yeah.
Do you guys remember from 9.1, day 1, what we talked about, like this forms?
find out where it starts
And
then you.
we
go
are
to
gonna do
opposite.
something like that a little bit later,
Okay.
but I mean just in terms of like the shape.
Oh. Triangle plan.
Yeah, it is gonna be a triangle. In particular, we talked about how
Oh, it's a sum of the.
it's gonna be the diagonal, right? So I think this is the picture that we had. In our notes, we had this vector and we had this vector, u and v, right? This was u, this was v, and I said it was gonna be the diagonal of, yeah, the parallelogram, right, formed. So this would be the parallelogram if you put them all together. So it's the same thing as your vector AB plus your vector BC and how that equals AC. Okay,
Oh.
so if you are in physics, you probably are used to drawing it like this, and that's fine. Okay, if not, I'm just showing you how you know where that's gonna go, because it's gonna go in between your two vectors. Okay,
Which
All
way
right.
do you want us to do it?
whatever way works for you. So,
Because, like, we do the head to tail method. like,
Yep,
it's
so
like
that's
one
fine.
showed us.
yep, it's fine. Okay, and then we're trying to find, bless you, the true velocity. Okay, so we talked about the true velocity and how the true velocity is going to be the vector that is the resultant vector, so the swimmer plus the river. So if I'm going to add those two together, first I actually have to make the two vectors. Okay, so for the swimmer, the magnitude is 2. What would the angle be? Susanna, what would this angle be if you're going straight east? Nope. So the angle. So think of this, if I put this on my unit circle, right? What degree would this be at? 0, right? So this would be 0 degrees, and this would be the sine of 0 degrees. So the cosine at 0 is what? 1, so 2 times 1 is going to be 2. The sine at 0 is 0, so 2 times 0 is going to be 0. So what does this vector represent?
Velocity of the swimmer.
Without
Perfect. Okay, so say it one more time, Jake.
The velocity of the swimmer.
Okay, so this is the velocity of the swimmer. Now we're going to do the same thing for the river. Okay, so the river is flowing at 3 miles an hour. And then Luke B, do you think you can tell me what the angle would be for this? Okay, well I'm going over it right now, right? So still pay attention to me, even if you did it a different way. So if you think of this as on the plane, right? You're trying to find this angle. What would this angle be? Close. It'd be negative 90, right? Because you'd be going backwards, so you could do negative 90, or you could also say what? 270. Okay, so either one of those is going to be fine. Okay, and then 3 times the cosine of 270, the cosine is 0, the sine is negative 1. Remember, those are from the unit circle. Are you guys okay with those points? Okay, so then 3 times 0 is 0, 3 times negative 1 is negative 3. And then what I'm trying to find is the resultant vector, which is r plus s. So 2 plus 0 is going to be 2. Okay, so I'm adding the 2 and the 0. And then I'm adding the 0 and the negative 3, which is going to be negative 3. So the two components are going to be 2, negative 3. Now, do some of you know how you could figure out that the vector was 2, 0 just by looking at the vector for this one? Yeah, Ethan?
Since it's directly east and directly south of the two vectors, you already have vertical and horizontal movement.
Yes, you already know that the horizontal movement for this is going to be 2, and then are we going up anything? No, so it would be 2, 0. Okay, for this one, you know you're going down 3, that's why it's negative 3. Okay, and then you're not going anywhere left or right. So you could reason through that one.
Can you just look at it and know you go 2 to the right, so it's positive, and down 3, so it's negative 3.
Right, yeah, because if you're doing the head to tail, you're going to have your the next thing it says, how is true velocity different than from true speed? And this is something that we talked about yesterday at the beginning of class. This was your bell work. So we talked about how true velocity is going to be the resultant vector. So when I say the resultant vector, okay, in this case, your true velocity is the river plus the swimmer, but I didn't want to give those variables because sometimes you have an airplane and wind, okay, or sometimes you have the boat and the current. So the resultant vector is always the object plus the force that's on that object, okay? So velocity is a what? Velocity is a,
Speed and direction.
which is a vector, right? So velocity is going to be a what?
Vector.
Okay, we'll try it one more time. Velocity is going to be a what? Vector. Okay, so that's why you want to have your true velocity as a vector. That's different from the true speed because the true speed is the magnitude, so your result is going to be a number.
So, yeah, isn't velocity a direction?
Yep, and a vector is too.
Yeah.
So the vector is giving you the direction, which I know.
So, that makes like that problem.
Yes. Yeah.
Not like the tangent because that round would be much harder.
Right.
But if you did that, would that be the true speed?
Yes.
Okay.
Yes.
And then can you repeat the part where you said the object and then like
Oh,
It
with
says
the.
the vector.
Oh yeah. Okay. So I said yeah. The true velocity is always going to be the object plus the force that's acting on the object. So if the object's an airplane, it could be the wind. If the object was a boat, it could be the current. Or if it's a swimmer, the force of the water. So it's always the object and then the force acting on the object. Did some of you find the true speed and the direction for this? Just accidentally. What did you guys get for your bearings? Okay, so, okay, yes and no. So first, this is our picture, right? So I know I'm going to be going somewhere in the southeast. And so if you got like 330 some, do you know what angle you found? This angle. That positive angle is what you found. Okay, so if Michaela, if you want to know this angle here, you could just subtract that from 360 and then just put your correct bearings on it. And there's a couple different ways you could do it.
So this is
wait,
the.
so we want the angle between S and
Yeah, if you're finding theta, then you could just do the tangent of theta. This is what we did yesterday, right? We could do the tangent of theta equals -3/2, right? And if we do that, the inverse tangent,
-56.
yeah, you got -56.30
.3.
degrees. Now this is in what quadrant?
4.
Okay. And look at my vector. Is my vector in quadrant 4?
Yes.
Yes, but I'm not going to label my bearings like this. You can do it a couple ways. You can say 56.31 degrees south. Yeah, good. South of east.
Could you do
Or you could do east
56.3?
56.31 degrees south. That would be fine.
And we didn't have to do that though.
No, you didn't have to. I know some people did, so I was just showing you.
Question for that?
Pardon?
What's a question for that?
Like what would it ask you?
Yeah.
It would say find the direction that the swimmer should head.
wait, can you explain again why you went 56 I just said
56. So see how this is your vector,
yeah.
your true velocity?
Yeah.
So to find that direction, you can do the tangent of theta equals b over a.
Yeah.
So your b is -3, that's 2. You're just going to find the inverse. And when you find the inverse, you'll get the -56.31, which is giving you this angle right here.
Oh,
So then you can say 56.31 degrees south of east.
okay.
All right, so for your next one, it says, suppose in example 2, that your swimmer is going where? or the current's flowing at 1.2 miles per hour due south. In what direction should the swimmer head in order to arrive at a point due east of his starting point?
Was this the opposite one?
Yeah, so do you guys remember like the shore one that we talked about yesterday?
Oh god.
Yeah, that was a little confusing. So this is going to be similar to that. And let's start by drawing a picture. And I just wanted to say some of you guys did such a good job on your homework, just extending your thinking and what you did in class. Okay, and if you're ever having trouble figuring something out, find a way to make what you tried visible to me. So that could be drawing a picture, that could be showing me your calculations, even if they were not correct. Right, so example 2, the current is still flowing south and it's at 1.2 miles an hour due south. It says, in what direction should he head in order to arrive at a point due east of his starting point? So, in what direction? That means I'm going to have to find theta. Okay? And think about where the swimmer started. So I'm going to use this picture.
Then he started.
Yeah,
the
yeah.
origin.
So he's still going 2 miles an hour. So if this is where he is, okay, if this is the shore, would you guys agree that he started somewhere over here? Okay, so if he started somewhere that way and he wants to go to a point that is east of that, okay, I'm going to say, I'm
Isn't
going
he
to,
just going where he's going already?
right, but he's headed in a different direction now. Okay,
Does
so,
anyone give it to us? Oh, that's what we're trying to find. Is the direction.
yes.
It changed the force.
Because this is the way he was headed, but really, this is him, right? This is him here. This is where he's
But he
actually
wants to
going.
go east.
Exactly. He wants to go east, which means what direction is he going to have to swim in order to go east?
Northeast.
Yes, he's going to have to swim somewhere in this direction. We don't know where. Okay, so I'm going to put this on my grid.
So it's a lot of like, what do you call it? Common sense, sort of. Like
It's
you
a
gotta
lot
think
of
through
like
it. Yeah.
analyzing,
That's-
right?
that's what
So this is going to be my north, south, east, west. I never eat soggy waffles. And what we're trying to find, this is my swimmer. He's still swimming at 2 miles an hour. But what we're trying to find is this theta value. Because if he wants to go somewhere that's east, that current is going to be pushing him south. Okay? And for this too, if you want to use a head to tail method, please feel free to do that. Sometimes I think the head to tail method is nice because you can visualize, like if it's going down, you can put this arrow up here, which I think sometimes is helpful. But using this method, if these are our two vectors, I know that my resultant vector is going to be somewhere in between them. And I'm not super picky about where you put this, but it should be
But
it
doesn't-
should be the diagonal if you're thinking of this as, and really it would look more like this.
Doesn't he want to go due east though?
Yeah, so we're talking about the actual one.
Oh, the one.
Yeah,
before?
so your actual one, and really you are going to be going somewhere here. This is just your resultant vector. Okay, so this is going to be the swimmer plus the river. So he's just going somewhere, yeah, due east of where he started. Not necessarily directly east, but somewhere due east of that point. Does that make sense?
Sort of.
Okay, we'll keep going because once we talk about the components, I think you'll get that. And again, just remember that whenever you're adding the two vectors, the one that's in between them is going to be the diagonal of the parallelogram that it would form. Okay? All right, so, yeah. Actually, here, let's do this. Well, let's imagine the parallelogram. If this is my parallelogram, well, okay, the hard thing about this is we don't know theta, right? So everything I'm doing here is an estimation. So if I estimated this was my parallelogram, then gonna be really close to east, I'm just not necessarily gonna be directly there.
Because you're going more
Okay.
And that's where he's
north than
trying to go?
east.
And that's where he'll actually go. He has to swim this way so that the river pushes him this way. He has to swim northwest so that it pushes him east.
I'm just confused at why it isn't just right on east.
Yeah, I'm also confused by that.
Like, if he's trying to go due east, I understand that he's swimming upwards so the force comes down on, but you like are drawing it underneath east. Like, why is it just
Because
straight on?
I'm just trying to line it up with my picture, and we don't know where our theta value is. So depending on where theta is, because at my theta value, it looks like I put it in the middle, right, around 45 degrees.
Yeah.
But that's not necessarily gonna be the case. So when we have an accurate picture of this, we're gonna have an accurate place of where my vector's gonna be. So the visual is for you to understand that your vector is gonna be in between there, and he is gonna be at a point that is due east of where he started. Okay, and you could actually put it directly on the east. That's not gonna matter as long as you understand that that's his true direction
Yeah,
and
it's
not
just
the,
Visualize it.
yeah, and not the swimmer. Okay, so let's go ahead and do the swimmer vector. So for the swimmer, he's still going at 2 miles an hour, but we don't know what the theta value is because that's what we're trying to find. That's the direction that he is swimming in. Okay, not actually, this is gonna be what he's swimming in, his direction, but not the actual place where he's gonna go. So we don't know theta, that's okay, we're just gonna leave our equation like this, and we're gonna calculate the river. So the river is now 1.2 cosine of, Luke, what's our angle? Luke, what's our angle? Yes, you. You need to come sit right next to me.
You also have 2 loops.
Okay, so if you're working ahead, then follow along with me. Because this is the same question I asked you last time. That's why I asked you the
No, we're
question.
in it. That's why.
He's literally said the same thing he said last time. There you go.
That was extremely counterintuitive.
Okay, so for negative 90, your cosine is still going to be 0. And for this one, you're going to have negative 1, so negative 1 times 1.2 is negative 1.2. So if you guys were here yesterday, this is similar to yesterday in that we're going to create the resultant vector, and we're going to have an expression. So when I add these two together, I'm adding the horizontal component to the horizontal component. So if I'm adding 0, okay, because we're adding the river and the swimmer, so this would just be 2 cosine of theta. And then I'm also going to add my vertical components. So here's my vertical component, here's my vertical component. If I add them together, I'm going to have 2 sine of theta plus a negative 1.2 or minus 1.2. And does anybody think they know what the next step is going to be?
Look at them.
Okay, you're going to set it equal to what?
0.
Okay, so let's talk about how you know what's being set equal to 0. So we want to swim towards the east, okay? If we're swimming towards the east, what types of forces are going to knock us off our path?
North, south.
North and south. So I don't want any forces coming from the north and none coming from the south because then that will knock me off my direction. So what I want to do is I want to make my vertical component 0. Actually, I wrote out the explanation, so I'll show you that first and then I'll solve it with you. So in order to head due east, we want the vertical component to be 0 because if it wouldn't, it would push us, the swimmer, either to the north or the south. And in, a way that you can think about it is you can think about if you're trying to head somewhere horizontal, it's a vertical force that you don't want. And if you're trying to head somewhere vertical, like north or south, it's the horizontal force that you don't want. Okay, so if we're heading to the east, we want our vertical component to be 0. So we're going to take our equation and yeah, so this is going to be our vertical component. I'm just going to take that and set it equal to 0. and I'm gonna solve for what?
Theta.
Yeah, I'm just gonna solve for theta, okay? So I'm gonna take 2 sine of theta.
It's not a good
No, thanks.
Sorry.
I didn't wanna
Trying to
cut people out trying to do that, but I got you. Okay, so now what we're gonna do is solve, so I'm gonna add 1.2 to both sides. Yeah.
Cosines still the same.
Say it again.
Is the two cosines like staying the same?
Yes, so we're not gonna worry about the 2 cosine, which is the horizontal part, because the horizontal part is definitely gonna be there and it's definitely gonna be positive. It just isn't gonna be a set value like we know that the vertical component will be.
Are we gonna have to, okay, this is gonna sound bad, but do we have to show this much work, or can we just like, cause literally it's like a formula, because it's whatever the vector thingy is, like, you just set it into the
Are you
same-
saying that you drew a different picture?
No, I didn't draw a picture at all, I just plugged it in.
Oh, yeah, that's fine. Okay, and then once you solve, you should have got 36.87.
Is that it?
Oh, that's the angle he wants to swim at.
Yes, so that's gonna be the angle that he wants to swim at.
So then we can plug it back into his,
Yes, if we plug that 36.87 back in, that would be the vector that when you
Yeah, if it
added
was
it with
asking-
your river. Yes.
if it was asking for like true speed or whatever.
Yes, exactly, exactly. And for this, I'm just gonna have you guys round to the nearest hundredth. I think I said this at the beginning. Because on your quiz, I'm just gonna say round everything to the hundredth, so you don't have to worry about switching back and forth between everything. Just always round to the hundredths. Okay, so we'll just make that standard. So this theta value is gonna be north of east. Yes?
Could you please send me a report to the office for a moment?
I sure will.
Thank you.
All right, and then, or if you wanted to say north 53.13 degrees east, that would be fine as well. Okay, so you could choose. Yes.
My question is, I did that problem
In a different way.
in a very different way for a lot less work.
That
Right?
I will look at your work and I will tell you.
I did it this way, like,
Yeah, as long as you're showing, like, as long as everything I can follow on your paper, then that's good. So I would err on the side of putting more than less if it's different, but as long as you have like your equations, then it should be fine. All right, guys, we really gotta move on because we still have this back page to go.
Oh.
Okay, so the next thing we're gonna do is talk about the force. Okay, so the force is going to be the push and the pull on an object. I know. Let's focus on this. Okay, Okay, so a force is going to be the push or pull on an object. The resultant force is the vector sum of the forces that are going to act on an object. So because it's the vector sum, we are going to end up adding those together. And then equilibrium is going to be the state in which opposing forces are balanced. So if you have balancing forces, what that means is when you add them together, actually maybe you know. Do you guys know what the vector would be if you add them together and it's in equilibrium? Yeah, 0, 0. Yep, it would be 0. Okay, so this, for example 3, it says the forces F sub 1, F sub 2, all the way up to F sub n are acting at the same point of P. Those are said to be in equilibrium if the resultant force is 0. And what that means is if f sub 1, f sub 2, all the way up to f sub n, if the sum of all of those is 0.
Oh boy. This
We
sounds
did
fun.
that in SST.
What?
So what we're going to do is first we're going to find the resultant forces acting at P, and then if we need an additional force for them to be in equilibrium, then we're going to do that too. Okay, are you guys done with the first part? Okay, good, because we have to keep moving. So for part A, the resultant forces, the sum of them is just going to be adding up your horizontal components. So if I add my horizontal components, I'm adding 1, 1, and negative 2. What's that going to be?
0.
0. And then negative 1 plus 1 plus 1 is going to be what? 1. Okay, so then that is going to be my vector. So on your homework, you do just have to put 0, 1. I'm just showing you that the way we got that is adding all of those together. So now I want you to think about, if this was going to be an equilibrium, what vector would I add to it?
0.
Exactly, 0, negative 1. And then I just wrote out y. So we would call this the fourth force because you already have 3, so the next force you would need would be the fourth one. And that's because if you added these together, 0 plus 0 would make 0, 1 plus negative 1 would make 0, and then everything would be in equilibrium. Okay, so the additional force is always going to be opposite of the resultant force to produce your equilibrium. So let's say your vector was 5, negative 3. What would the other vector you want to be?
Negative 5 positive.
Okay, yeah, negative 5, positive 3. So it's always going to be the opposite. Now, there's a special case, and that's if your vector is 0, 0. So if your vector is 0, 0, then what you would write is no additional forces needed. Okay, so if you added the vectors and you got 0, 0, for part B, you would just write no additional forces needed. Because it would already be in equilibrium. Okay? All right, and then for the next one, I actually have to show you I have to give you the measurements. Okay, so your diagonal or your first angle is 45. What's that?
Were you just saying what
For 2. Jake, where's your thing today?
Sorry. Hey, I've been good for like the past.
Very good, I know. Okay, so for 45 degrees is what you should have labeled here. This is 15 degrees. This is your first force. This is your second force. Are you guys done with that part or no?
where did you get that from?
Why is there no additional force?
Because it's
That,
in 0,
so
0.
that's for a different example. So I said unless the resultant force is 0, 0, you wouldn't need an additional force to get to 0, 0 because you're already there.
Okay, then what is the part B?
For part B, you should have 0, negative 1.
That's what gets it to 0.
Because if you add these two together, if you do the sum, then it would be 0, 0, and then that's equilibrium.
So you're finding, so you're trying to get to 0.
Yes, exactly. So whatever you would add to get to 0. Yep. So because 0 plus 0 is 0, and 1 plus negative 1 is 0, that's why this is our other force.
Yeah.
I've just been confused.
Okay, and then your magnitude is 5. Stay with me, please. So your magnitude is 5, and then your magnitude for this is going to be 3.
Does it tell you that, or are you?
No, I'm giving this to you. So it just takes me too long to do that on the computer to get everything right where I want it to be. And so that's why I'm giving this to you. So this is the entire picture that you'll be given. So now what you have to do, it's the same directions, but you actually have to find your force vector, which we can do pretty easily by knowing the magnitude and the theta value. Okay, so Alex, for this one, what's our theta going to be?
45.
Yeah, so this is just going to be the 45. And you can always round this because you are going to be adding. So if you're going to be adding, you don't have to worry about writing this as like 5 root 2 over 2. You could if you wanted.
Can I just do the?
Yes.
Yeah. Okay.
Okay, so you would get 3.54 and 3.54, and you can just round that to the nearest hundredths. So that's your first force. Okay, and now we're gonna do our second force.
So it'd be 3 sine 15.
That, nope,
Cosine- Wait, how do you know it's cosine or sine?
that, so horizontal
Oh, X
is,
and Y.
yeah, so horizontal is always gonna be cosine.
Sorry.
That's okay. Okay, so Megan said 15, and for this one, it's not gonna be 15, but yeah, Megan, you know why?
195.
Okay, how'd you get it?
Because theta starts at 0.
Okay, yeah, so you have to think of it as theta starting at 0. And so what you're doing is this whole angle here, which is the 180 degrees plus the 15.
195.
But Megan, I don't know if you were thinking, is there another way that you could do it
No.
in physics? Okay.
No, I just said it wrong.
Well, because I had other people do -3 cosine of 15, because it's going
I
around
don't
this
know
one.
that.
Okay.
Well, I mean,
Then don't worry about it. Yeah, just use your theta. Okay, so once you compute this, you should get -2.90. Yeah, nice job, Cal.
Well, I won't do this. But yeah, I got the right answer.
Okay, and then, all right, so now what we're gonna do for part A is we're gonna add our forces together. So we're gonna add our F1 and our F2, and that's gonna be our vector. Okay, so when we add those together, we're gonna get 0.64. So we're adding the horizontal components, and then we're gonna add the vertical components.
I actually really enjoyed this.
Okay, good. And, you would get
2.76.
thank you, 2.76. Okay, so Luke, I'm gonna give you a chance to redeem yourself, and you're gonna tell me the answer for part B. So what should my third force be if I wanna have this in equilibrium? That's it, nice work.
Good job.
Luke.
Yay.
And is that the answer? F3?
That's
Yes.
the answer.
Okay.
Yep, and then so because we had two forces before, this is the additional third force we would use. Okay?
And you just, however many forces you have.
Yes.
That's all we do?
Morgan, give me a time.
1:30.
112.
Cal. That was
Okay.
scary.
So, example 4, my lovely students just want to show their love and appreciation. So
That
they
is a
decide
beautiful-
to
I'm gonna make
hang
That's really heavy.
a 50-pound heart. I know you guys are strong. Okay, so a 50-pound heart weight from a string in front of the school, as shown in the figure below. Okay, so this is going to be the 50, and you guys don't have the other labels in there. I'm going to give them to you. So this angle is 58 degrees.
Okay, this is going to be a problem.
I know. And we're going to do it a little bit different than the physics way. So
I like
if
your
you
way.
are thinking of a different way to do it, I want you to write down both ways.
I write down your
So, what are the T1 and T2?
It's like F1.
Okay, so for your notes, if you're doing it another way, that's fine, but on your notes, I want you to have this way, and then on your test and on your homework, if you guys want to do it the physics way, that's fine. You don't have to write both, but I want you to have an example of how we did it on your notes, okay?
Alright.
Okay, so there are a couple of things that we need to know in order to set up the equations. So, yeah, were you gonna tell me one of them? Are you guys gonna tell me one of them?
9.80.
What's that?
9.2.
Oh, yeah, so that's something else that's gonna be different. Okay, so, yeah. Alright, so tension. What we're doing is a tension problem. Okay, so we're trying to find the tension in the string. So it's important to know that the up forces are going to equal the down forces. Okay, because if not, there would be motion. If the weight force was pulling down, what would happen to the weight? It would fall, right? Okay, if I exert a force on this desk going up, right, the up force is greater than the down force, and that's why the desk moves up. So what we want them to do is we want them to be equal to each other.
That's the last
Okay.
something horizontal.
You're very strong.
To like the
Okay, so this is or else there would be motion.
left of the
Yeah.
It says something, does it say two horizontal?
Both horizontal components.
Yes, two horizontal. Okay, so we are going to use our horizontal and vertical components. So we're going to use the magnitude times the cosine of theta, the magnitude times the sine of theta. Now both horizontal components have to be equal, or else again there would be motion, but this time it would be swinging side to side. Okay? So you don't want there to be different forces. The tension has to be equal in order for that object to stay in the middle. Okay? And then what we're going to do is we're going to set up a system of equations, and we're going to solve using substitution. Now I know you can also use the law of sines. Okay, yep, and so you're welcome to do that. I'm going to show you how to set up a system of equations and then solve them using substitution. Okay?
Oh yay, substitution.
Okay, so the first thing we're going to do is we're going to draw a couple of pictures. And
116.
the first one I'm going to draw with you, and then I think you'll be able to draw the second one from there. Okay, so let's do that. Okay, so what I'm going to do is I'm just going to redraw this part. Now you don't have to redraw it, but I like to show you that I'm isolating this part. Or really, I can show you right on here. Basically what you want to do is you want to make a triangle.
With what? With one side?
Okay, so if you think of this side here, do you know what type of angles these would be?
36.
Isosceles.
Oh, acute.
Interior angles.
Oh, I don't.
So this would be 58 degrees as well. And see how this would form a triangle here?
Dude, yeah, dude.
Okay, so I'm just gonna write that down below because I just want more room to write without running into my picture, okay?
What are we writing?
That I'm just gonna draw that same thing. So I'm drawing, this is my tension 1. Okay, so this is still my vector. This is still my 58 degrees. And then I'm just showing you that this is 58 degrees, so that's exactly what I drew there. Could I draw that any tinier? Sorry.
God, this is a complicated process.
Okay, so I want you to understand that what we're doing is we're drawing the horizontal component and the vertical component. So now if I look at this, I know that my horizontal component is going to be the magnitude, and my magnitude is just the T1 tension multiplied by the cosine of 58 degrees. That's my horizontal component. Do you guys feel like you know what the vertical component is?
Q1 sine of 58.
Exactly. I'm going to just write it this way.
Oh my god. I'm crazy.
I can see.
It's a nice finger.
Okay, so T sub 1 sine of 58 degrees is the vertical component. And then T1 cosine of 58 is going to be the horizontal component. Okay, so I want you to do the same thing with T2. Yeah, with the other side.
That's fine.
Alrighty then. T2. Yes, T2. Okay, and then we can still label both sides. Alright, so the bottom will be T sub 2 cosine of 35 degrees. Vertical is T sub 2 sine of 35 degrees. Okay, are you guys with me so far?
Yes.
Okay, so now what we're going to do is go back to what I was just talking about. So the first thing I said is up forces have to equal down forces. The next thing is that both horizontal components have to be equal. So two things have to be equal here. So for step one, I'm going to write out the steps too, so when you look back at this, you can, you know what to do with whatever numbers you have. So you're going to set the horizontal components equal, and then we're going to solve them for a variable. Now you don't have to solve them for t sub 1, but in my experience, students like to be told what to do sometimes. And if you have a method, like you can always solve for t sub 1, then they like that. But technically you could solve for t sub 2 as well. Okay, so if we're going to set my two horizontal components equal, my first horizontal component is t sub 1 cosine of 58 degrees, and that's going to equal t sub 2 cosine of 35 degrees.
Plus it can't be moving, so it has to be equal.
Yes, yep, because if the left tension was a little bit more, then the heart would be pulling towards that way. Okay, bless you. So now I'm going to solve for t sub 1. So if I solve for t sub 1, how do I move the cosine of 58 degrees over? I divide it. So I'm going to have t sub 2 cosine of 35 degrees divided by cosine of 58 degrees. And if you want, you could also rewrite it like this, or think of it like this. This is t sub 2 times the cosine of 35 degrees over the cosine of 58 degrees. Because you know how if you had x over 5, how that's the same thing as 1/5 x, like when you're doing slope? This is going to be the same type of thing. So t sub 1 is going to equal t sub 2 times the cosine of 35 degrees over the cosine of 58 degrees. Now here, I'll let you decide. If you want the exact answer, you should use this. But this is also a number. And so if you wanted to use that t sub 1 is approximately, if we divide those, you get about 1.55 t sub 2. I wouldn't mind if you did that. Okay? Now that wouldn't be the most exact answer, but I know it is a complicated process, and I'm fine if you are willing.
Is that the answer?
Oh, well then what's t sub 2?
Not yet. Okay, so we have to set up a system of equations, so we just set up the first equation. Now we're going to set up the second equation.
How many are there?
2.
6.
So the second thing is that the up forces have to equal the down forces. So the down force is going to be the 50 pounds. Do you guys know what the up forces are going to be?
50 pounds.
No?
0 pounds.
Well,
So it has to equal
the vertical components.
variable component.
Sine
They'll
35
equal 50 pounds, okay? So you have two vertical components. This is going to be the sum of the vertical components. So we're going to have t sub 1 sine of 58 degrees plus t sub 2 sine of 35 degrees, and that's going to equal 50. So now that I have an equation for t sub 1, my step 3 is going to be to plug t sub 1 into equation and solve.
Oh, I do not have enough room for this.
No, I'm sorry. Okay, so if I plug in t sub 1 we said was equal to t sub 2 times the cosine of 35 degrees over the cosine of 58 degrees.
Dude, how does this make any sense?
Stay with me.
I'm so confused.
So you just call for cheese.
But
Okay, so now that you have this, notice how you have t sub 2 in both of those? Okay, so what you can do is multiply them together. And if you want, like I said, you could turn these into decimals. Yeah, if you guys were absent yesterday, I need your homework in the bin or else it's late, so make sure that you turn it in there. I am gonna check your homework on Monday, so make sure you show all your steps, and again, we'll check that in class.
What's our homework?
It's online, and then finish watching this video.
Miss Vessel's 6-hour class, please go to Miss Russell's room. Miss Vessel's 6-hour class, please go to Miss Russell's room.
Okay, so once you plug in your T sub 1 value,
Danny May.
okay, so once you have this, notice that T sub 2 is in both of these. And what we're going to do is just factor that out so we can do all of this at the same time. So we have T sub 2. If we factor it out from here, we have the cosine of 35 degrees over the cosine of 58 degrees times the sine of 58 degrees plus, and then if I factor T sub 2, hey, you guys can just sit anywhere, but can you be quiet because I'm recording this? And this is the sine of 35 degrees equals 50. So now when I'm solving, I can go ahead and I can do this on my calculator to get an answer to solve for T sub 2. So I'm going to show you how to do that. Okay, and when you have this much stuff, it's really better if you kind of do it piece by piece. So the cosine of 58 equals, and then we're going to multiply that by the sine of 58. And we're going to add that to the sine of 35. Alright, and so this is approximately 1.884. So that's what I'm going to divide each side by. But I'm going to keep that value in my calculator. So when I do this, I'm going to do 50 divided by my answer. And then I'm going to get about 26.5. Now, using a system of equations means that our last step okay, so once you have your T sub 2, you're going to plug T sub 2 into original equation for T sub 1. So we know T sub 1 is equal to T sub 2 times the cosine of 35 degrees over the cosine of 58 degrees. And I'm going to plug in the 26.5 or 0.53 times the cosine of 35 divided by the cosine of 58. And I'm actually going to use my exact value that I have in my calculator. So I'm going to first multiply it by the cosine of 35. And then I'm going to divide that answer by the cosine of 58. And yeah, I get 41.01. And that is going to be my force. So my force for both of those are in pounds. Okay, and then remember, I'm checking your homework on Monday. Thank you. Bye.